Question 13. So we remember from question 12, the architect desires a channel as a facies section, which is a beam and torsion problem. Now we're going to look at modifying the design, so perhaps we can put an edge beam in it, effectively to design out the torsion in the beam. And the edge beam is a channel with toes down, which is narrow in section. The edge beams are cantilevered with backspans, cantilever action, and we're going to try and achieve what the architect wants. 200 by 90 PFC for the backspan. We have the tapering section, and we're giving the IYY value for the channel toes down, and the IXX, which is the channel normal orientation. The figures, section 2 figures in chapter 2.9, figure 2.9.8 and 9, and various figures 2.3.2 and so on. Question 13a. So we're going to set up the elements. This time we have a backspan. Now first of all, we're going to look at the edge beam with the loading on it to see what the deflection of the edge beam is. So the IXX is given as 315 centimeters to 4. For figure 2.2.3, we've got 1 kilonewton, which is a beam with a point load mid-span. That's PL cubed over 48 EI is the formula for the deflection. And with consistent units again, we make the calculation for the 1 kilonewton load, gives us 2 millimeters, which if we think back to 12 is low. Question 13b. And we're going to look at the influence of the supports, which are the backspanning tapered beams, which are a tapered section with a PFC as a backspan. We're going to make a conservative assumption for the backspan, so it's a 0.5 kilonewtons as a reaction for the PFC toes down from 13A, and it's 3 meter backspan, 1.5 meters. The I value for the tapered section 150 is given pH cubed over 12, which comes out to 337. The PFC behind is a lot stiffer, but we're going to assume for the sake of argument that it's actually the same as the tapered section. It's conservative, very conservative. So the deflection as a pure cantilever is PL cubed over 3 EI for the tapered section. We fill in the values with consistent units, come out to 0.81 millimeters. So now we can prorata this using from section figure 2.3.5 from chapter 2.3 with a backspan of 2L, and this comes out 8.5 over 3 times 0.8, which is 2.3 millimeters. Question 13c. Finally. So we're now going to sum the deflections to see whether we believe this is satisfactory. We've got 2 millimeters from the beam, and we have 2.3 millimeters at the tip from 13B, so the total overall deflection, you add these together, you get 4.3 millimeters. Now this is based on superposition, which is an important principle, and then we will go on to look at relative stiffnesses. Question 13D. We're going to take the two cases and look at the concept of relative stiffness. So from question 12b, we had a deflection with a PFC of 158 millimeters, and if we take 13c, the example, the total deflection that we had was 4.3 millimeters. So we're going to look at the relative stiffness of the two cases, and in doing this what we do is we take the reciprocal of the ratio of 4.3 to the addition of 4.3 plus 158. So it's 158 plus 4.3 in the brackets, comes out total of 1 divided by 0.03, which is 37, which is significantly stiffer. Thank you for listening.